I'm going to start. Good evening. Today I'm going to be talking about families of connected self-similar sets. These are interesting because you have a space there where the self-similar sets are sharing the same topology, and so you can extend analysis on all this area I'm going to be showing you later. So I started working on getting interested in fractals when I was a teenager. It happens that my hometown is Figueres, and there is the hometown of Salvador Dalí. He was having this artistic intuition of fractals, that there is this piece of art, the Face of War, that Bernat would like to show it in his talks. And that's the idea of having a nested. In this case, that the attractor is a disconnected Cantor set. Instead of ternary. So when I was 16, I spent the whole summer taking pictures of nature and trying to find these, to figure out different functions that they have. And for the case of fractals, it's mainly extending the space in a continuous way. Ferns and also plants that are like a binary tree or a ternary tree. It's easy to model, but that was my earlier motivation to study it. And that's when I read the books of Bernat and then Michael Barnsley, Fractals Everywhere. That was a good start. I went to study physics at University Autónoma Barcelona. And that's why, because at this point I was interested in applications. And I heard about the theory of Laurent Notaire, a French physicist who was trying to study this, the fractal space-time using different things. I also read the book of Stephen Wolfram. There is a chapter there about trees. So, and then I heard about other studies like the fractal flows and stuff like that. And then applications, that was important for me to get motivated for the subject. Leonardo was one of the first to study trees in a mathematical way. He had some concepts of scaling, and you can actually read the notebooks that were never published, but he has some laws that are still like used by botanists in some cases. So I moved as an exchange student for 1 year at UCSB, and there is when I started to actually make computational explorations and using this tree vendor from the co-founder of Wolfram Research, Theodore Gray. So that, because I read some books, there's Mario Livio is an astrophysicist, so he had a popular book about these topics, and I had read that when I was a teenager. So I knew there was some relations there, but I was not seeing the connections. Mario Livio was taking these golden binary trees from a book from the Hans Balzer. He's from Switzerland, and he has a very nice book as an introductory thing. You can give that to high school students, and they're going to be understanding how it works, and there is many problems. So that's a good way to get started. And I was making these computational experiments with an asymmetric tree, and when I close this loop, here, when you close the loop, then you get this pattern. So I was struck by the beauty of it. And at that point, I was the following year, I was at Heidelberg University in Germany, and that's when I got started to read more about the history of fractals. I was using mathematics also to make 3D models, and using a printer, I was printing some earlier models. This using the tetrahedral structure with the scaling factor 1/2. And so I was doing that, and I tried to see if there was someone working on that at Heidelberg University. And that's when I contacted Susanne Kromke so she's the head of the visualization and numerical geometry group there, and she had done some renderings earlier on with some of her students, and she has also collaborated with Götz about this castle in Italy, Castel del Monte, and she had done these nice renderings back in 1991. So I knew how to develop some of these pictures in there using this fractal. Here is using 8-branched fractal tree. So, but then I knew also a way to unfold it, and I was using this notion of folding the branches in a symmetric way. And when you fold it, you're going to see that the leaves of this tractor, it's connected, so it's a string. It's a Jordan curve in the space. And when you reach the 180 degrees, when it's completely folded, you get this kind of generalized Koch curve with this 8-fold symmetry. And it matches exactly to the plan of the Castel del Monte. So when I contacted her and I was telling her about this story, she was very surprised, and she gave me completely freedom to do a project during my Erasmus there at Heidelberg. So I read the classics. Cantor is one of them, and then von Koch was interesting because when you read the original article, he was trying to find a geometrical way to explain the Bertrand function, but that's why he developed the Koch curve. And for example, if you cut the boundary, you get the Cantor set, the classical one. And then Paul Levy was looking at what von Koch had done, and he was taking so these are fractals that were drawn about 100 years ago. He was hand drawing it. So he was taking the von Koch curve and then unfolding each triangle to get what is now called a Levy curve. So that's the idea. And Bernat Mandelbrot considered himself a disciple of Paul Levy. In his book, he had Levy curves, but he was using the notion of a fractal tree, and he had some earlier work about when the tree is self-contacting, when it's not a Cantor set. Right here, the leaves are a Cantor set, disconnected, but he was interested at looking at the point when they just intersect. So you have the linear extension of the trunk for the symmetric binary tree. And when that happens, you stop there. So you get the right scaling factor. So here I'm showing you when you are rotating the branches, and then you have some critical points when you get interesting fractals like the H3, that's the A4 paper proportions, and then there is another critical one at 135 degrees. So in this area you had Koch curves generated by L3. So later, in 1999, Michael Frame and Bernat Mandelbrot published this popular article in the Mathematical Intelligencer, and they were talking about this self-contacting fractal tree for the case of the binary keys. And then I read that, and then I saw that there was a PhD thesis by a Canadian mathematician, Tara Taylor, and he used methods from computational topology and different things, and she found many interesting facts. One of these facts is that there are like 4 golden symmetric binary fractal trees, and they have some interesting symmetries in there. So that's what she was doing, looking at the different symmetries. But what happened is that when you take the symmetrical branch of this initial gasket I was showing you, you get this Levy kind of curve with the tree. You take 5 copies of it, then you end up with this boundary that's exactly the same as before, but it's related to Penrose tiles, the tilings. And also if you cut the boundary, you get what is called a golden Cantor set. There is an interesting paper about that from 1998, and there is some interesting number theory properties of this. So because of these relations, I was starting to spot a way to to generalize these fractals, because they had some kind of duality between the Gauche curve and the Levy curve. So that's when I extended it, and I was using the diagonals of the regular polygons to extend the theory and get different things. So that's for binary trees. So here you have the typical Gauche curves, but then you can generalize it to other types of Gauche curves. For 3 branches, you get these patterns there. Here is the one for the Castel del Monte I was showing before. And then for 4 branches, you get other Gauche curves. And so on. So you get all these dots there is when you have n-fold symmetry. So another thing is that I was noticing that the gasket, in this case for the H3, is the 2-gon gasket. For 3, you get the Sierpinski triangle, and then the reverse of the Sierpinski triangle. So I'm just gonna skip it here, but so that's the reverse of the Sierpinski triangle, and that's just for binary. Now I'm gonna show you for the ternary trees, and that's the motion there. So you get the geometric curves for this blue part here. That's the right now. What's going on? And for quaternary trees, then it's the same, but you have to change and get so you get these pieces-wise smooth curves to jump from one family to another. It's like a phase transition when you get to the joining parts of that course. So that's the equations. I'm not going to go to the details, but that was published back in 2013. Here is the same plot, but as a Cartesian plot, the angle and then the scaling factor of the branches, and you see that it matches nicely. So that was for what I call the down binary fractal trees, symmetric. But you have to look at also the equations for the upper ternary binary fractal tree. So that's for 3 branches. When the limiting point is the Sierpinski triangle, and you can work out all the equations as well by looking at these pieces-wide smooth curves to know the right scaling factor. So then I realized that this set, this boundary was studied earlier by Michael Barnsley and his student Hardin. There is a PhD thesis about that object there, and also independently, Steve Wolfram was also studying this set. So the idea is that you can extend it to other types of fractals. So instead of having just like 2 transforms that are mirror symmetric, you can have a transform, for example, that's 180 degrees rotation from the initial branch. So that's the one we were looking before. It's piecewise smooth. If you are in this area, you have a Cantor set. The leaves are disconnected. What's called the tip set. And for the other family, when you have a branch that's 180 degrees opposite, that happens when it's minus C. You get this other set, and you have disconnected Cantor sets in this area, and when you get to the black area is when you get a tip set that's connected. So when I met the guys at Wolfram, I was doing a project for 3 weeks, and I was extending these families in 2D for 3 dimensions, and you can also get some nice equations in there. So I'm going to skip that. You can also find golden 3-dimensional fractal trees, and that's when I met them in Baltimore. That's the same time I met also Bob in 2014. So the things that I started working for Wolfram, and until 2017, that I contacted this group at University of Barcelona. That's Núria Fagell is the head of the holomorphic dynamics group, and I tried to learn a lot of different tools that they were using. I did a master thesis there. And the motivation is because I get some emails from people who were interested in this kind of sets that Bill Thurston was interested before he died. But so he knew the relation that you can get these attractors, but he never. I mean, there is different publications I can tell you later. One is Sarah Koch and Danny Caligari, who worked on that. But what I wanted to do is to use these tools using the notion of a tree to extend it to non-symmetrical ones. For example, for this element, you get these two pair of equivalent relations. So you have these branch paths connecting the piece in red and the piece in black. And for the upper relation, you can get a family when you can have this connectivity in this part, at this point. And then for the lower relation, you get another family. So that's the idea. Here you can see the Mathematica manipulate when you have these parameterizations. There is some spaces when you have overlappings, but there is a subset and an area there where the topology is just this point. And that's for the lower relation. And the idea is that you can compare these two families, and we have the typical one, that's these two relations, but at some point it appears that there is other relations. In this case, they satisfy the same equivalent relations, and that's the tree you get. So you can tile the plane. It's similar to what Michael Barnsley was telling us yesterday. So there were some elements that were starting to pop out. So at this point, I get to the motivation to what I was doing and the reason why I was introducing this notion of complex tree back in 2017. So the idea is very easy. So you start with a geometric series, but instead of just using one complex number, you use two numbers, and then you start having all the combinatorial possibilities. And I'm imposing that the initial n-ary branches have to be smaller than one. You don't want to have the tree to escape to infinity. So the idea is that you have the alphabet and with all the letters, and then you have this map that I call the geometric map. You take the initial complex valued letters to be 1 and 2 for the binary case, and I'm using these values as an example. So that's the first nodes for the tree, and then you start like, for example, 1, 1 is just going to give you this piece. And then 1, 1, 2 is you take black, black, and then red, and so on. For the empty string, it's going to be mapped to 1. That's the root, and that's when the letter is when the word is finite. Then I call these points nodes of the tree, and for an infinite word, then I call them tip points. And one example is just the 1, 1, 1, 1. It's spelling this way, and then for 2, 2, 2, it's the one. But you can also have closed expressions for periodic or eventually periodic words. For example, that's 1, 2, 1, 2. You get to that point, and that's the algebraic expression of that tip point. So as a self-similar set, this is just a family of n maps for binary. This is just these two linear maps, and what it's doing is just like shrinking by the factor of your complex number, and then the argument is going to give you the rotation, and finally I'm adding this one translation. So that's for the F2 transformation. You can get the same for the F1. So the union is the self-similar set. That's the basic idea that all of you must know. But so from studying that, you can prove things. For example, in this case, you can prove easily that it's a Cantor set, and it's not intersecting. So the main idea using this notion of complex tree was to impose tip-to-tip conditions. So I was, for example, I'm going to show you one case when I'm trying to glue these two nodes in there with these other two, just as a pair way. So here you have the expressions. And you end up with a system of two equations with three unknown variables, which are these three branches. And when you solve it, you find out that you leave the black branch as your unknown. And then the C2 has to be always 1/2 in the real axis. And then C3 is just a Mobius transformation, 1/4Z. And then when you get that, you can start like perturbating your system. So here you have the three main pieces, and the connectivity between them, the intersections between them, it only happens in these 2 points, D and E. So the idea is that you can add an epsilon neighborhood, or you can perturbate these three, and you're going to get the same topology for this area. And that's when I introduced what I call a stable set. So the stable set is, well, first your family is defined by imposing that they have to be smaller than 1. So that in this case, it's giving you that has to be the absolute number of the parameter has to be bigger than 1/4. So it's defined in these annulus for this family. So that's the white dot we had for this example. Now I'm just going to show you some other examples going a bit down. You can see that the fractal is being morphed, but then they still have the same topology. And now I'm going a bit left, and at some point you have this intersection. So I have to add to what I call the topological set. I have to add this relation in there that corresponds to these two relations, which is just going 1/1 in black, and then always 2, and then 3/3, and then 2. So that's when you get when that happens, when you have an extra equivalent relation, I color the point in my space in black. So what I was doing is I was imposing other relations, and when you do that with this parameterization, you get a polynomial. So we're just crunching roots of polynomials and getting different solutions. And for each solution, I was coloring it in black. So you end up with this set, and that's when you lose the structural stability. So for the white regions here, all the self-similar sets are connected in the way that you impose by definition, but they are stable in the sense you can perturbate it, and it's going to be having the same topology. It's interesting for this family specifically because you have that the boundary of these stable sets are piecewise smooth, and you can prove how they are and see different things. Here I'm just going to walk around one piece of this piecewise smooth boundary. That's starting with the Sierpinski triangle here, and it's going down until we reach a critical point. You get this gasket thing, and then going this direction until you get this other case, and then up until here, and then we just tangential intersection until you get to this classical one. So I'm just going to skip that. So that's the basic idea, and then there is some symmetries. When you go this way, the other branch is going to the other direction. So, but that's you have some symmetries that you can simplify your analysis in there. So that's the basic idea. When you're moving in these white regions, then you have the same topology. So if you know how to do analysis in one of those, then you can extend it to the whole white area. Now, for the Sierpinski triangle, you have these three pair of equivalent relations. So if you remove this one instead of this one, you get another family, and this family is one that's related to the classical Rasi fractal. You get this shape there. Actually, I bring a copy of my set that was printed at ICERM 2 years ago, and here I'm going to show you an animation for this other family when you keep these relations. in there. So yeah, I'm moving from one Sierpinski triangle to the classical Rousey fractal. And that's kind of neat to have that. Finally, as another example, I'm going to show you what happens for the reverse of the Sierpinski triangle. So here the two relevant relations when they meet with the three pieces are these ones. So here you have that your branch goes down, and then that's 2, and then goes down again, so it's 2, 2, and then you start switching from black to blue, 1, 3, 1, 3, until you reach this other tip point, starting with 1, then 2, then 3, 1, 3, 1. So it's interesting because you end up with almost the same family as before, but now you have the red branch equal to -1/2. So it goes this direction. And now the boundary is not that neat. It's not piecewise smooth as before, but still you can make pictures of that and see that there are some Lamarck points with some algebraic numbers happening there. So it's and that's the reason why is that rough is because of the boundary. The boundary is no longer made out of straight lines as before, and so when you try to intersect or just touch the different pieces, the 3-level pieces, then you get these ins and outs that are not that easier as the other family for the boundary. So you see the idea is to have these wide regions where you have the structural stability, and that was the case for the symmetric ternary fractal tree that I was studying 10 years ago. But now for each curve, you can extend it and have a structural stability region. So that's the idea. I have now this way of extending for each smooth curve a whole region where you have the structural stability. You lose the mirror symmetry that we had before, but very interesting things can happen. That's for the Koch curve. You get this set. So that's for this piece in there. So in all these points in there, you're going to get a Koch curve which is a simple curve. It's not overlapping, so there is no loops. And that's for the other piece. For example, you get this other set in there, and so on. So in 2019, I went to this illustrating mathematics program at Brown University, at ISER, and then I got the chance to work with 3D printers, and I'm showing you a case where that's a binary tree, and it's actually overlapping, and the way it's overlapping is quite neat because it's happening in an exact way. There is these nodes that are connected at some point, so intersecting from one piece to the other, and that's the example in 2D. But you can find out the way how the boundary is defined, and that's using this notion of neighborhood maps that Michael Barsi was telling about, and that was introduced by Christoph Pan. But and then using also a notion of the college theorem, but using trees, it's much easier to understand why this piece stems from this part, and to get the right function, like the composition. For example, here it's just like 2 in red and then 1 and then red again. So that's going to be this piece. So you get the right thing. And then for 1, 2, 2, 2, you get this other piece. So that's the function you're going to be composing with. And then for 1, 2, 2, and 1, 2, so you get this piece there. So the union of them, they are going to give you this curve for the boundary. And I was using this technique to get these tilings, these partitions of the fractal. And you can actually use a laser cutter. At ISER we had a Glowforge, and that's where I had the chance to use it to cut some wood. And that's quite fast to see. And it's nice because you have some sequences of of these pieces that are exact. So you can see the different number theory things and stuff like that. But this is just one example, and here some colleagues playing with it. Another thing I did at Tyson was to play with the boundary equations. That's for the H3. So you have a way to get all the branches that are going through the boundary, but then rotating it, finding another interesting example. That's when you collide and you get this other curve. So that's another study. But I'm going to be stopping here with the initial gasket that I got interested with. And so that's the example with the laser cut version of it, or using the start, the 5-star polygons. I have some examples here. I believe that there is plenty of applications to be used, so that there is many things what we could do. But yeah, thank you. Yeah, when I met Bob, I was having this one 3D printed, so I gave him a copy of that. But that's another story. So here you have larger versions of the pins. And I was meeting David Cohen, who is making fractal antennas. So there is another field there to explore. But yeah. And at Bridges, I was presenting another family, maybe because I have time. I'm just going to introduce this other family. It's like the Sierpinski triangle, but instead of having the relations we were seeing, we are having these other two pairs of relations. So you end up with this connectivity, and it's looking more like Fern-like ternary tree. So that's for the symmetric case, and that's when you are like moving in this white area. You have a structural stability. So you can do many things there. You can also have the geodesics of that. And then, yeah, that's all. And then there is different theorems for complex trees, like the root connectivity. So there is one tip point going to the root. Then you have another tip point going to 0. And that's giving you some information about the structure of that. You can make the root connectivity set of that map, and that's a subset of the stable set. So, and you have landmark points as well. For example, this you have this asymptotic similarity with your self-similar sets and the root connectivity set for these cases. And then you can look at different things here. That's instead of looking at 0, you can look at the other parameters, and that's for the case of the Sierpinski triangle family. And because all the parameters are giving you a connected self-similar set, then you get all these nice shapes. There are no counter sets in there. That's it. Yeah, thank you.
Our schedule starts